Welcome to Learning with Philemon. In the radical substitution video, we saw that alkanes can be converted to halogenoalkanes via the radical substitution mechanism. In this video, we will explore another type of mechanism, nucleophilic substitution, to see how halogenoalkanes can be converted to alcohols. In the oxidation video, we introduced the concept of primary, secondary, and tertiary. In this video, we will only focus on primary and secondary halogenoalkanes that undergo bimolecular nucleophilic substitution, abbreviated as SN2. When the carbon bonded to a halogen atom X is bonded only to hydrogen atoms, not other carbon atoms, it is considered primary. When the carbon bonded to a halogen atom is also bonded to one carbon atom, it is also considered primary. Note that R represents a carbon-containing substituent, such as methyl, ethyl, etc. When the carbon bonded to a halogen is bonded to two carbon atoms, it is considered secondary. Now let's take a look at the SN2 mechanism. 2-bromobutane is a secondary halogenoalkane. The carbon bonded to the bromine atom is also bonded to a methyl, CH3 group, and an ethyl CH2CH3 group. Halogenoalkanes contain a polar bond. Bromine is more electronegative than carbon, so it pulls the shared pair of electrons closer to itself. This means that carbon is slightly positively charged, denoted by the delta plus, and bromine is slightly negatively charged, denoted by the delta minus. A nucleophile is an electron-rich species that donates an electron pair to form a bond with an electron-deficient species. In this case, the hydroxide ion is the nucleophile. It is electron-rich as it has a negative charge and electron pairs that it can donate. Remember that double-headed arrows in organic chemistry represent the movement of electron pairs. In this case, electrons from the hydroxide ion forming a bond with the electron-deficient carbon atom. This leads to the formation of a transition state, denoted by the brackets and the double dagger superscript. In this state, carbon has partial bonds with both the OH and Br groups, denoted by the dashed bond. Note that for a brief moment, the carbon is bonded to 5 groups. The transition state has a very high energy, so it is unstable. It cannot be obtained from the reaction like a product can. For more on transition states, please watch the videos in the energetics playlist. Eventually, the carbon-bromine bond breaks. The electrons from the carbon-bromine bond are taken by the bromide ion-leaving group. The products are formed, 2-butanol and a bromide ion. Note that the molecules in the mechanism have been drawn showing their three-dimensional shape. This is because the SN2 mechanism leads to an inversion of the stereochemistry. For more on this, please watch the video on optical isomers. Having seen the mechanism, let's now analyze why it is called bimolecular nucleophilic substitution. A bromine atom has been replaced by an OH group, hence the term substitution. This is done by using a nucleophile, in this case a hydroxide ion, hence the term nucleophilic. Two molecules are involved in the rate-determining step, the slowest step in the reaction mechanism, in this case the first step, hence the term bimolecular. This will be discussed further on the next slide. As the rate-determining step involves both reactants, the rate of the reaction depends on the concentration of both the nucleophile and the halogenoalkane. The rate equation will have the following format. The higher the concentration of the reactants, the higher the rate of the reaction. For more on rate equations and rates, please watch the videos in the chemical kinetics playlist. There are other factors that affect the rate of substitution reactions. The first factor is the halogenoalkane itself. Primary react faster than secondary, which in turn react faster than tertiary halogenoalkanes. In fact, tertiary halogenoalkanes follow a different mechanism, SN1, which will be discussed in the next video. This pattern is due to the steric effect. Bulky groups bonded to the carbon prevent the nucleophile from accessing the carbon. The nucleophile always approaches from behind the carbon-halogen bond. The fastest reaction occurs with a primary carbon bonded to 3 hydrogen atoms, the smallest groups. The leaving group also affects the rate of the reaction. As seen in the mechanism, a halide ion is formed. The more stable that ion is, the more readily the reaction occurs. The stability of the ion actually depends on its basicity. The more basic a species, the higher its tendency to share its electron pair. This means that the ion is more reactive and less stable. Iodide ions, I-, are the least basic, and therefore the least reactive and most stable leaving groups. Finally, the solvent, in which the reaction is conducted, affects the rate. SN2 reactions should be conducted in aprotic solvents. An aprotic solvent does not accept or donate hydrogen ions. Water is an example of a protic solvent. Nucleophiles can form hydrogen bonds, as denoted by the green dotted lines, with protic solvents. As the nucleophile uses its lone pairs to form hydrogen bonds, it becomes a weaker nucleophile. It will be less likely to use its lone pairs to form a bond with the electron-deficient carbon atom. Thank you for listening. To consolidate your learning, answer the questions in the description. If you haven't already, please subscribe for more content. Stay curious.